Hi everyone, this is Kalyan Kumar and welcome to Chemistry Tutorials. We were doing a series of videos on atomic structure. In the last part, that was part 5, we talked about the nature of radiation. We talked about the Maxwell's contribution to how spectrum is supposed to be, light is supposed to be electromagnetic radiation. We talked about what is wavelength, what is frequency, what is time period, etc. And in this particular part, part 6, we are going to look at atomic spectra, the spectra of atoms, both absorption and emission spectra. That is what we're going to look at into this particular part. Now, the first thing that we need to understand here is that in atomic spectra, when white light is passed through a prism, it is separated into light of 7 colors, which we call as Vibgyor or Vibgyor, depending upon how you pronounce it, or radiations of different wavelengths. Basically, you see the visible region into 7 principal colors, which are Vibgyor: violet, indigo, blue, green, yellow, orange, and red. So this is what happens when you pass it through a prism, or you can even pass it through what is known as a diffraction grating. You'll understand greater detail of what is diffraction and what is diffraction grating when you study optics and physics. But right now you can understand that a diffraction grating can mimic a prism. The pattern obtained by splitting or sorting out the radiation into its component wavelengths is called a spectrum. So spectrum means when we separate these colors and we study which particular color corresponds to which particular wavelength. And of course, we are not only looking at colors, we are even talking about invisible region. But right now, let's focus on the visible part. The spectrum of white light, when analyzed by a spectrometer, which is an instrument that indicates the wavelengths and frequencies of individual components of a radiation, is a continuous spectrum, suggesting that white light is made up of all possible wavelengths or frequencies of radiations. For example, if you look at sunlight and pass it through a prism, you'll only see 7 colors. But remember, there are a lot of other radiations in sunlight, in natural light, which are not visible to us, like ultraviolet, infrared, X-ray, gamma radiations. Everything is out there. So when you do it with a spectrometer can analyze all of that and can even show up those invisible radiations in the form of line spectra, which we'll just study in detail now. So remember, white light consists of a continuous spectrum. The visible part is always there, of course. In spectroscopic work, a term called wave number is often used. It is defined as the number of waves contained per unit length. Now, let's understand what is wave number, because we quite often talk about wave number. Wave number is nothing but the number of waves contained in a particular unit length. Just like frequency is the number of waves contained in a particular interval of time, that is 1 second. Similarly, wave number is the number of waves contained per unit length, which could be centimeter, millimeter, meter, or whatever. Now, at lambda centimeter distance, so that means if, let's say, the wavelength is lambda and that value of lambda is in centimeters, so at lambda centimeter distance you get 1 wave, because 1 lambda is equal to 1 wave. So what would be the number of waves in 1 centimeter? It would obviously be 1 by lambda waves. So the wave number is 1 by lambda. So this is a continuous spectrum. And now we are going to see a demonstration of how a continuous spectrum appears to be. So let's have a look at the demonstration. So this demonstration is about a continuous spectrum of an incandescent bulb. And incandescent bulb is a bulb which produces light on heating, which most of the filament bulbs do. And this emits all radiations available in sunlight. So this is the incandescent bulb, and we are going to study its continuous spectra, the spectrum emitted by this. For that we need diffraction grating. This is a piece of plastic paper, but it's not an ordinary plastic paper. It has got lines printed on it, which are black and transparent, and these are very fine lines, and the amount of lines range from 10 to 20,000 lines per inch of the paper. So this is equivalent to a prism to generate the kind of spectrum that you would see of sunlight or an incandescent bulb. So what we're going to do is we're going to place this in front of a camera and then show you the spectrum of the incandescent bulb. So this is the incandescent bulb, and the grating is going to be placed right in front of the camera, and that's it. We have placed it. Now you notice that at the center is the incandescent bulb, and on either side, because of the diffraction grating, you notice the spectrum of the incandescent bulb, and it's a continuous spectrum. It contains all the spectral lines in the visible and in the invisible region. And as you can see from the left onwards, on the right side you see blue to red, and on the left side you see again blue to red. It has the entire VIBGYOR region in it. You may not see all the colors, but it has the entire VIBGYOR region in it, going from the higher energy to lower energy. Now that we have seen the demonstration, let's talk about something else. If a gas is heated, it emits light. When this emitted light is analyzed in a spectrometer, the spectra obtained consists of a series of well-defined sharp lines, each line corresponding to a definite wavelength or frequency. These line spectra are characteristic of atoms, and we call them as emission spectrum. Let's understand this. What this basically tells you is that if you take a gas, let's say you take a monatomic gas and you heat it. Now it's not necessary always to heat it. You can pass current to it. The idea is to excite the electrons. And when the electrons get excited, very soon they fall back. And when they fall back, of course, we are going to study the details of this when we study the different models of atom which are yet to come. But the idea is the electrons get excited. We know electrons are there inside an atom. They get excited up and they come back. When they come back, they emit a particular amount of radiation, whatever they had absorbed to go up. And if that falls into a particular visible region, we'll be able to see it. If they fall into a non-visible region, yet it would be identified by a spectrometer, we may not be able to see it. Now, the idea is that when this emitted light is analyzed in a spectrometer, the spectra will obtain consists of a series of well-defined sharp lines. It's not continuous. That means in an atom, the electrons will not absorb any wavelength. They'll absorb specific wavelengths, and it is these specific wavelengths which they will emit. So whatever energy they are absorbing, they are going to emit that. So they are going to absorb and emit eventually discrete wavelengths, discrete energies, well-defined values of frequency. And we call this as an emission spectrum. Hydrogen atom contains only one electron, and the spectrum is the simplest to analyze. The spectrum of atomic hydrogen consists of a number of discrete lines in the UV, some in visible and some in IR regions. Each line corresponds to a particular frequency or wavelength. The space between the two lines represents the frequency range in which no radiation is emitted by the hydrogen atom, because that amount of energy it did not absorb. It absorbed only particular energies. Lines observed in the atomic spectra of hydrogen are grouped into several series called the spectral series. A group of lines appearing in the UV region is called Lyman series. That in the visible region is called Balmer series. In the IR region, there are three: Paschen, Brackett and Pfund series. So Balmer series is of interest to us because it's about the visible part. So let's see a demonstration of the emission spectrum of 4 different elements. In this demonstration, we're going to see the emission spectrum of 4 elements, and we're going to use a discharge tube to see the emission spectrum. We're going to fill a discharge tube with these elements. We're going to pass electric current, which will excite the electrons to the higher state, and when they come back, they emit certain colors. We're going to see that now. So this is the discharge tube. The first element that we're going to use is mercury, and we're going to pass electric current through this, and the mercury vapors will get excited, and when they get excited, they would tend to emit certain particular wavelengths. So we're going to see which wavelengths these are. So let's place it in the place where we can pass the current through it. We'll switch off the light, and so the lamp is switched off. We don't need the lamp. This is the mercury vapor discharge tube. Right now there is no spectrum here because we're only looking at the mercury vapor there. The moment we put the diffraction grating in front of the camera, you'll be able to see the kind of lights it emits. It looks bluish, but we need to see the spectral analysis of this to check what are the various colors it emits. So let's put the diffraction grating now, and you'll be able to see what colors this particular vapors are made up of. And as you can see, it's blue and green. Blue on the left side, because from the left to the right on the right side, and on the left side from the right to the left, the energy will increase. So it's made up of actually blue and green spectra. The next one is nitrogen, and this is the nitrogen, and as you can see, the diffraction grating is placed, and you can see now a range of colors starting from violet to turquoise, and you can see green, you can see some yellow, you can see some orange in it, you can see red in it. So basically this is what the nitrogen is looking like. The next one coming up is the neon, and this was used earliest in neon signs. As you can see, it's bright orange, yellowish orange, and in fact the lights it emits are also pretty close to this color. You can see yellow, you can see orange, you can see red. So it is the emission spectrum of neon, which almost resembles the neon filament itself. And the next element that we will be seeing after this would be the most important one, that is hydrogen, because we're going to study the hydrogen spectrum in detail. This is hydrogen in the discharge tube. It has a reddish haze around it, and as you can see, it's got a dark blue on the leftmost. Let's look at the right spectrum. The dark blue, then you have a light blue or bluish green, you can say, and then you have a red at the end and a little band at the center. The electrons have been excited up and they are coming down. So this is the visible region of the hydrogen spectrum, emission spectrum. Alright, now that we have seen the demonstration, let's go ahead and now we will talk about what is known as absorption spectrum. When white light is passed through an element in the gaseous state, it absorbs certain discrete wavelengths, which is characteristic of the particular element. The light that is transmitted consists of wavelengths not absorbed by the gas. This is called absorption spectrum. Now this is exactly the reverse of the emission spectrum. What we are trying to do here is, now here the gas is not heated. No energy is given. The only source of energy is light. So when white light consisting of a continuous spectrum is impinging on a gas, the gas is going to absorb energy. For a gas, it doesn't matter whether you heat it or you pass light to it. If it gets the appropriate amount of energy, it will absorb it. So it absorbs a certain amount of energy and the electrons get excited. And when they get excited, since these energies are absorbed, whatever light is transmitted out, in the transmitted light, these energies are not present because they have been absorbed by the gas. And what will happen is, when you analyze the spectrum, you will see certain discrete black lines which correspond to the wavelengths of those radiations which have been absorbed by that particular gas. And the wavelengths absorbed by the gas appear as dark lines in the resulting spectrum. So let's have a video on this. Let's see a demonstration of what is absorption spectrum. In this demonstration, we are going to talk about the absorption spectrum of sodium ions. So we will be taking sodium bicarbonate, and which is a solid, and we will heat it, vaporize it, because we always study the spectrum of vapors. And when sodium vapors are formed, we will pass light and check the absorption spectrum. So this is the instrument that produces the light, and we are going to put a tiny filter in it so that we can get a very thin slit. Otherwise it will be very dispersed, and we adjust the aperture so that we can get a very thin slit in this. And now we'll place the diffraction grating here. This is the diffraction grating, and as you can see, the continuous spectrum of white light, it's continuous, nothing is missing. This is sodium bicarbonate, and we are going to take this and put a flame in between so that we can vaporize it. And when we vaporize it in between, you will notice that in the spectrum some dark line will be formed. That is a line which this is absorbing from the white light. So this heating is done only to vaporize it. As you can see, the dark line, somewhere in the yellowish and orange region. This dark line is because the sodium ions are absorbing this particular wavelength. You can see this in detail now. It's focused, and these dark lines are appearing whenever the sodium vapors are formed. Since they are not continuously formed, so you don't see the dark line continuously. So as soon as they are formed, they absorb that particular light of that particular wavelength, and that goes missing from the spectrum. Alright, now we talk about, in 1988, Johannes Robert Rydberg, a Swedish physicist, established an empirical equation defining the wave number of each of the spectral lines in the hydrogen spectrum. This was called the Rydberg's equation. Now, this was an amazing piece of work. In fact, I would say that this work was so important that probably it was this work that led us to a better model of an atom, which was later on proposed by Niels Bohr, which we'll come to later. So what we need to understand here is what this guy did. He looked at the hydrogen spectrum, either emission or absorption, they would be the same. And the only difference is in the emission spectrum, you will only see discrete lines of spectra which are emitted. In the absorption, the exact same places would be dark lines. Now what this guy did, he identified the wavelength of all the radiations emitted by hydrogen atom. Let's say he's talking about emission spectrum. So he looked at all the wavelengths emitted by hydrogen atom, and then tried to create an equation in which you would be able to find the wavelengths of all those radiations which are being emitted by hydrogen atom. One single equation that can give you the value of wavelengths of all those radiations which are emitted by or perhaps even absorbed by hydrogen atom. Now, using this equation, one can calculate the wave number of any of the spectral lines appearing in the spectrum of a hydrogen atom. And remember, it was totally empirical, it was totally experimental, no theoretical knowledge was used. And of course, he never went on to explain why it is like this. He simply found it, and believe me, getting something even empirical is a big deal. The equation goes like this: 1 over lambda, which is known as nu bar or wave number, is RH, some constant, into 1 upon n1 square minus 1 upon n2 square, where n1 and n2 are natural numbers. They can take value from 1 to any value, and they are natural numbers. So obviously they can't be negative or they can't be 0. And RH is some particular constant. So substitute value of n1, n2, any value of n1 and n2, appropriate values, whatever value wavelength you will get, you will find that that line has been emitted by the hydrogen atom or absorbed by hydrogen atom. Where n1 and n2 are natural numbers, n2 obviously greater than n1 because you don't want a negative value for RH, and RH is called Rydberg's constant. It is the most accurately derived value for a physical constant. Now that has flown, the value of Rydberg's constant is 1.097 into 10 to the power 7 meter inverse. Rydberg worked out his equation after being strongly influenced by Balmer's equation, in which n1 is equal to n2 with an uncalculated constant. Of course, one of the primary reasons for the rejection of most of the atomic models was that they failed to explain Rydberg's equation. So this was the work of Rydberg, and this was one of the most important equations that led to the final model of an atom, which was proposed by Niels Bohr. And after that, of course, the entire gamut, the entire look and feel of the atom changed after Niels Bohr proposed. But Niels Bohr was able to use his own model and get this particular equation theoretically, which proved that what he had done was absolutely correct. So that is the end of this video. If you have any questions, queries, doubts, suggestions, comments, please drop them in the comment section below. Now, if you have not subscribed to this channel, please do subscribe immediately, as I'm going to post lots and lots of videos in this channel, and you'll be able to get the intimation the moment I post these videos, the moment you subscribe to this. And you'll be able to access my channel much more easily when you subscribe, because you will have it in the subscription list. If you like the video, please do hit the like button. This is Kalyan Kumar signing off. Have a great day and thank you for watching.